Okay, so I've started looking through some of your drafts for this assignment here. This is the one where the detector is trying to detect bombs, and we want to know if it does better than 25%, if it does better than chance. And some of your drafts are not great. Let's just say that. So remember, there's a list of steps that you just got to do that are all required. Let me open up the assignment. So if this thing does better than 25%, it's promising, and we probably want to invest some more money in it. If it doesn't, if it can't do better than just guessing, then we just want to let it go, and we're not going to put any more money in it. Notice there's a question here that you have to answer. This little follow-up question. That should be part of your final solution. Should we put more money into this thing? Is it better than 25%? So your first step, required step, define your variable. And I'll help you with that. Let P be the proportion of bombs this thing detected. Then you've got your sample statistics. I've got a sample size and a number of successes. There's my N, there's my X. From those, I can get my P hat. P hat is always X over N. Then I write my hypotheses. Your hypotheses are complete mathematical sentences, not just numbers. Your null hypothesis is this thing is just guessing. Like, oh my God, the answers are right here. Like here are the part. when I uploaded this, I didn't realize the answers were attached. Now, this is not a complete solution. Like, they didn't bother to write out. They didn't define the variable, let P be the proportion of bombs this thing detected. But like, most of the work is here. There's your null hypothesis. There's your alternative hypothesis. This says the thing's just guessing. This thing says, oh no, it does better than guessing. You've got your sample proportion of success. So you're going to write all that out. Then we're going to use our calculator to find our p-value. Like, they tell you what the p-value is right there. That's what you're going to get, but plug it in your calculator. Draw the picture. A picture is required. Now, I've mentioned this a couple of times. There are two different ways to approach hypothesis testing. One is by looking at z-scores and rejection regions, and one is by looking at p-values. We use the p-value approach. So I don't care about that z-score at all. Don't care. They gave both in this solution. I care about the p-value. Now, they don't give me an alpha level here. They don't tell me how big is big enough. So, like, in the real world, you get to pick your own alpha level, and the industry standard is 5%. Sometimes people will use 1%. Sometimes they'll use 10%. That p-value is bigger than all of those. Like, tell me what alpha you're using, but your only choices are 1, 5, and 10%. Tell me which one you're using, and then that's bigger than any of them. Doesn't matter which one, you're going to fail to reject the null. Now, you got to write out what that means. What does that mean? That's a required step. Everything I'm saying here is required. You're always going to write out this thing in words. Either we do have strong evidence for the alternative, or we don't. When we reject the null, then we accept the alternative, and we say we do have strong evidence, in this case, that the thing can detect more than 25%. When we fail to reject the null, like we just did, then we don't have strong evidence of this. So your next line, a required step, would say, we do not have strong evidence that this thing can detect more than 25% of bombs. We don't have, another way of saying that would be, We don't have strong evidence that this thing isn't just guessing. So there's no, it doesn't work. Like I'm telling you the answer, the machine don't work. It ain't finding the bombs better than guessing. So we're not going to pump any more money into it. So make sure you go back and answer this question. I kind of just told you the answer. Okay, I want to do, like I showed you this last time, that we've got all these different practice tests here with solutions. Someplace there's a video of at least this one. It's in one of the weekly overview pages. But I'm going to do, like, I've got so many old tests. We're going to go through another old test 3. I'm not going to do every problem, but we'll do a few of them. Okay, like I'm not going to do this one for you because I really, really like this question. Knowing what all the letters stand for. Like that's going to be on your test. You got to know what all the letters stand for. These are good questions. What happens when you increase your sample size? What does that do to your margin of error? The bigger the sample, the smaller the margin of error. When your sample size increases, the margin of error decreases. If you theoretically went to an infinite sample size, which would mean your entire population, then there's no margin of error at all because you don't have a sample, you have a census. You've talked to everybody in the population. So when sample size increases, margin of error decreases. If your confidence level goes up, if you're doing a confidence interval and you go from 95% confident to 99% confident, you're more sure of something, there's got to be a trade-off. And that trade-off is your margin of error also goes up. The more confident you are, the more wiggle room you have to leave. So as this increases, the margin of error also increases. Okay, knowing what all the letters mean, like that's really all stats comes down to. So somebody's done a sample. They got a bag of M&Ms. There are 82 M&Ms in their bag and 47 of them were green. I want to know what percentage of them were green. P hat is always X over N. So that would be 47 over 82. So 57%, or as a decimal, or I was going to write this as a decimal, what was it, 0.573. Similarly, if P hat is always X over N, X is P hat times N. So it's a similar problem, just working backwards. That's my P hat. I have to write that as a decimal, 0.80. My sample size was 40. So how many successes were there in the sample? 80% of 40 would be 32. Okay, now let's do some problems. Remember, on your test, there are only 4 problems. Like a question might, or the test might be 20 questions long, but there are only 4 types of problems. 1 proportion test, 1 proportion interval, 2 prop test, 2 prop interval. That's it. So the first thing we want to figure out, are we doing a test or an interval? Confidence intervals always say confidence interval, always. Hypothesis test won't always use the words hypothesis test. But a confidence interval will always say, find the confidence interval. Read this question, it doesn't say confidence, in fact, it literally says right there, hypothesis test. So this is going to be a test. Now I got to figure out how many groups do I have? Am I comparing 2 groups or do I only have 1 group? So if you read the question, we've only got one sample right there. That's one sample. So this is a one crop test. I think that's button 5 on the calculator, but don't quote me on that. I don't have these memorized. Okay, so first thing we're going to do is define our variable. Everything you're going to see me right here is required. Let P be the proportion of, so without even reading the question, I know I'm going to have to write that. I got a sample of 430. They were given ibuprofen. So there's my population, people with arthritis given ibuprofen. Everybody in the population has that. In this case, everybody in that sample, but that's my population. This group of them did something, had side effects. So there's success. Population is people with arthritis given ibuprofen. Success had side effects. So let P be the proportion of people with arthritis let me spell arthritis right, on ibuprofen, on Advil, with side effects. Okay, so that's a required step. You always have to do that. I know I'm going to keep saying this, but a lot of people don't do it. All right, now we look at our sample. Every sample is going to have an X, an N, and a P hat. They're always going to give us 2 out of the 3. And like literally, just like we did here, we're going to find the missing one. They're always going to give us N. They have to give us N. That's 430. X is the number of people in the sample, not the percentage, the actual number of people in the sample that had side effects, 24. Okay, so then P hat will be 24 over 430. So we get our trusty calculator out. It's 430. So 0.558. I'm going to round that to 3 places. 0.0558. I guess 4 places I'm going to round it. Let me make sure I wrote that right. Yep. Okay. All right. Now, if more than 4% of the population is successful, has side effects, they're going to put on a better warning label. So we're going to use a hypothesis test. This sample says, hey, yeah, it's more than 4%. Look, that's like 5.5%. That's more than 4, but it's just a sample. Samples vary. That's not proof. That could just be a statistical fluke. Samples vary. We're going to figure out what's the probability of getting that sample if it's actually less than 4%. So we write our hypotheses. Hypotheses are always complete mathematical sentences, not this. My hypothesis is not 4%. It's that P equals 4%. Then the alternative, which is what the sample suggests, says, no, it's not. It's more than 4%. Why did I write more than? 2 different reasons. That's bigger than 4. And it says more than right there. Okay, we draw our picture. Drawing the picture is a required step. And the reason for that is it catches a lot of mistakes. Right here in the middle, that's our P naught, that number right there. So 0.04, P naught. What we believed before we did the sample. My sample was way up here. P hat. Here, I'll write this here. P naught equals. That's an ugly equals. And then we're always going to always shade a tail, always. So I'm just shading this little tiny bit here. If my sample were down on this end, I would have shaded down here. Notice that I shaded that direction. Like think of that like an arrow. I'm gonna draw that arrow again. I shaded that way. Look at that symbol and look at that. That's why I want you to draw the picture, because you'll catch a lot of mistakes right there. Because if you get this wrong, that symbol wrong, everything goes wrong. Okay, that's our setup. Now we're going to find the right button on the calculator. We're not doing any of these by hand. This is the moment when I told you you needed to have a graphic calculator. This is why you need it. So we're going to go stat over to tests. And I'm looking for what I said, one prop test. Remember on test 3, you're only going to use 5, 6, A, and B. That's it. Those are the only buttons you need. Test 4 in a couple weeks, it's 2, 4, 8, and 0. You don't need to know that yet. Right now, 5, 6, A, and B. And if you're not sure, like, look, if I go here into button 6, it's asking for a lot of stuff that I didn't write down. I didn't write down an X1 and an N1 and X2. I didn't write all that down because that's the wrong button. Now I want button 5, one prop test. Okay, I wrote all this down. There's my P naught, 0.04. X was 24. N was 430. And then what did I write for my alternative? Watch this. I'm going to show you something. I'm going to do this wrong. I'm going to pick the wrong alternative. I picked less than when it was supposed to be greater than. Hit calculate. If you ever get a p-value bigger than a half, you goofed. That's 95%. You're never going to get a p-value of 95%. Ever. Because look at what we shaded there. I didn't shade 95%. I shaded a tiny little fraction. That's another reason I want you to draw this picture so that you can look at that and go, well, that can't be right. You're never, ever, ever going to get a p-value bigger than a half. If that happens, you probably picked the wrong alternative. So I go stat, over to tests. I want greater than. Notice, by the way, also, those are the same number. You're never, ever going to have two different numbers here. Okay, I get 0.047. So that's my p-value. I wish the calculator made it more obvious that this is a capital P. Those look too similar to me. By the way, there's our p hat again that we found at the beginning. This is the one. I don't care about the z-score. This is the one I want. My p-value, my probability. That's a probability. It can't be bigger than 1. And it'll never be bigger than a half even. Okay, so our alpha level is 5%. That's smaller than 5%. That's less than alpha. Less than alpha, reject. Repeat that to yourself 100 times. Less than alpha, reject. Like if we were in class today, I would have everybody repeat this in like a chorus. Less than alpha, reject. So that's my next. Everything you see here is required. Now I have to make a conclusion. Am I going to reject or fail to reject? I'm going to reject the null. Okay, what does that mean? That means I can accept the alternative. So your only choice is never accept the null. Your only choices are reject the null, which lets you accept the alternative, or fail to reject the null. Never accept the null. Okay, so now I'm going to write this out in words. I just said I'm going to accept that. Every time you're going to write this thing right here in words, by either saying you do have strong evidence for that or you don't. I just said I accept it. So we do. I'm going to type this because we have strong evidence that more than it. I find it easiest when you're writing these to start with that symbol. Instead of writing the proportion of people, but it's easier just to say more than 4% of your population was successful. Of people, I'll actually type it all out. On ibuprofen have side effects. Now, normally I'd be done. That's what I was trying to answer. But there's this hidden right here. I really like these. This hidden follow-up question. Do they need to put a stronger warning label on? They said if they can find evidence that more than 4% are having side effects, they're going to put on a warning label. We found that evidence, so we're going to put on the warning label. They should put on the warning label. This is a complete solution here. Everything you see. Like, I guess you don't have to write that right there. Everything else is required for a complete solution. Okay, let's look at this one. So pause, read the question, figure out what kind of problem we're doing. Is this a confidence interval or a hypothesis test? It's an interval, and I know that literally says right there, confidence interval. Okay, now how many groups do we have? Am I comparing two groups, or how many samples did I do? Don't just count the numbers. Sometimes people will go through and they'll go, oh, well, there's 1, 2, 3, 4 numbers. So it must be 2 samples. Come on, that's not a number. That's just the year we did this. That's not a number. That's just part of my population. There's only 1 sample. It's right there. So this is a 1 sample interval, 1 prop interval. Decide that before you start just jumping in and throwing numbers in a calculator. Okay, we got to define our variable. Required step. Let P be the proportion of, and like I wrote this before I even finished reading the question, of what? 12th graders that always use their seatbelt. My population is 12th graders. Female 12th graders, I should put in there. Let's be specific. That always use their seatbelt. I guess technically it's really female 12th graders that say they always use their seatbelt. I mean, they could be lying, right? But like, we'll go with it. That always use the seatbelt. Okay, now we have our sample. Every sample is always going to come with an X and N and a P hat. They're always going to give us 2 out of the 3, and we have to find the third. So we've got, there's my sample size, 1172 female 12th graders. How many of those wear their seatbelt, or say they wear their seatbelt? 744. Then P hat's always X over N. That's 744 out of 1172. Throw that in our fancy calculator. I already forgot the numbers. 744 out of 1172, I think, yeah. 0.635 will go. All right, now the calculator is going to do all the work for us. Back when I first started teaching this class, I used to make students do these by hand. Like find the standard error, find the appropriate Z star from a table, and then find your margin of error. Like we used to go through all that. And that's fine if you want to. But you got this button on the calculator that's going to do it for you. So why? Why go through all the work doing it by hand? Just go stat, over to test. Oh, I didn't go to test. Over to test and down to A. One prop interval. And look, they're asking for exactly the same stuff I just wrote down. X was 744, N was 1172. And they want a 95% confidence interval. I'm done. There's my interval. Like these are the easiest problems ever. 0.607 and 0.662, we'll call it. Now the hardest part is just interpreting that. No, read my words here. Construct and interpret the confidence interval. What does that mean? And it's always the same sentence. It's always the same. It's always we are whatever percent confident that between, don't forget the word between. Our answer here is a range of values. That and that. So let's write those as percentages, 60.7% and 66.2% of your population was successful. 12th grade females always wear their seatbelt. There's my interpretation. Now, like every time I use this test, people make this problem here, part B here, much harder than it needs to be. Sure, we could do this as a hypothesis test if we wanted to, but a confidence interval is the flip side of a hypothesis test. I've already done I've already done it. I'm pretty darn sure the real answer is between these two values. Is it possible that the real answer is 75%? It's possible, but I'm 95% sure, I'm actually more than that they're wrong. If it's not in the interval, you're done. Like I don't have to do a whole hypothesis test. No, I don't believe it. It's not in the interval. If it's in the interval, never, ever, 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 ever say you believe something. That's not what statistics is about. We're either finding evidence to support a theory or we're disproving a theory. We never prove theories. So if they said, I think the real answer is 65%, you would go, that's possible, it's in the interval. If they said 75, that's not in the interval. So like you don't have to do anything crazy here. Just say, I don't believe that. 75% is not in the interval. You're done. That's it. There's not a whole lot of work there. So it's only worth 2 points. Okay. Read this question. Test or an interval? It literally says right there, hypothesis test. It's a hypothesis test. How many groups do we have? Are we comparing two groups? Yes, we are. I've got men and women. I've got two different percentages. I've got two different sample sizes. I've got a population size, but I don't care about that. Notice, you've noticed I haven't checked the conditions on any of these. If you fail to meet the conditions, it's a boring question. There's nothing we can do. So we're not even going to bother with that. So that number is there just for checking conditions, but I'm going to ignore it. I don't need it. And this is a two-prop test. So we're going to compare groups. First thing we're going to do to find our variable. Never ever mention your groups in this line. Let P be the proportion. Maybe I should be typing this part. Probably go quicker. Proportion of. Who's my population? Who am I studying here? People that are taking this drug. What's success? What did some of them do? They caught a cold. So my population here is people. I mean, I could say men and women, but it's better if you don't mention your groups here in this line. Let P be the proportion of people on this drug who caught a cold. Okay, then we have our two groups. We got men and women. Each group is going to have their own X, N, and P hat. I think my calculator just crashed. I'll have to open that up. Don't decide who's group one yet. Like in the homework, they don't always do this. In the homework, they kind of randomly choose who's group one and group two. I find these so much easier if we get to choose who's group one and we pick the one that has the higher P hat. So 41%. These are my P hats. P hats are percentages or proportions. We got to write these as decimals though. So for women, it was 0.41. For men, it was 0.43. My sample sizes, I had 110 women, 230 men. Don't worry, the sample sizes don't have to be the same. Don't let that bother you that there were more men than women. Now we got to find our X's. So going down, we divide. See, look here. To get that number, I divided. Going up, we multiply. So 0.43. I'm going to write it this one first. 0.41 times 110. Oh, yeah, forgot my calculator. Sorry, you got to sit through watching this thing load. All right, so what we got? 0.41 times 110, 45.1. Now, some of the astute students may realize that something bad's going to happen, but let's just write that down here. And then similarly here, 0.43, right? It was 43, yeah, times 230, 98.9. And again, something bad's going to happen here in a minute. We'll deal with that when it happens. All right, we write our hypotheses. My null hypothesis is always that the two groups are the same. You could either write that as P1 minus P2 equals 0, or if you like, it's okay to write that as P1 equals P2. These two groups are catching colds at the same rate. The drug works the same for both. And then the alternative, if you play your cards right, if you always choose group one to be the one with the bigger P hat, like I did here, I chose them to be group 1, then your alternative is always going to be the difference is positive. Or alternatively, P1 is greater than P2. This says they're catching colds at the same rate. This says, no, they're not. Men are catching more colds. The proportion of men on the drug that caught a cold is bigger than the proportion of women on the drug that caught a cold. Okay, now we just, calculator does all the work. This is a 2-prop test. So I have to go to stat, over to tests. Oh, look, that's number 6. I don't have these memorized. I know it's 5, 6, A or B, but I don't have them memorized which is which. Oh, look, good. They're asking for exactly the stuff I just found. They're asking for the wrong stuff. You probably picked the wrong button. All right, so I'm going to type in the numbers I got. 98.9230. What was that? 45.1 and 110. And my alternative, greater than. I want P1 greater than P2. And I'm going to hit calculate, and I'm going to get an error. You can't have 45.1 women catching a cold. The X's have to be whole numbers. These two right here have to be whole numbers. So you just use normal rounding rules. Don't think, oh, I have to round up. Just use normal rounding rules. So that would round down to 45, and this would round up to 99. X's have to be whole numbers. So this was 99. What was N1? 230. 45, 110. Hit calculate. Notice these are now rounded. See, these were they lied to us. When they said 41% and 43%, they lied to us. They rounded a little. These were the numbers they actually got. And we fixed that by rounding the X's. We're not making stuff up. They did when they gave us these numbers here. Okay, the only number I really care about right here is the p-value, this one, 0.35. That's a gigantic p-value. That's huge. Big p-values are bad evidence. The smaller the p-value, the stronger the evidence. It's counterintuitive. Small p-value is large evidence against the null. Remember, it's like the null hypothesis is on trial, and the p-value is like, imagine you're on a jury for a murder case. The p-value is the probability somebody else did it. So if there's a 1 in a billion chance that someone else did it, that means the guy on trial probably did it. So small p-value is strong evidence against the null. Okay, we have a 5% alpha level. 35 is much bigger than 0.05. That's bigger than alpha right there. That's alpha. So we fail to reject the null. Smaller than alpha, reject. Bigger than alpha, fail to reject. Okay, remember, we're always going to write out the alternative. Every time, we're always going to write it. We're either going to say we do or we don't have strong evidence for this line right here. In this case, we don't have strong evidence. When you fail to reject the null, you don't accept anything. So we would say here, we do not have strong evidence that the proportion of men on the drug who caught a cold is more than the proportion of women. it takes longer to write the sentence than it does everything else. Who caught a cold is more than the proportion of women. And it's implied there, I mean, the proportion of women on the drug that caught a cold. Okay, now there's this follow-up question. You always got to look for these. Who's the drug more effective for? Well, in this case, we couldn't say. We don't know. The drug's supposed to prevent colds. So if men were catching more colds, we would say, oh, the drug is working better for women. But in this case, like, we don't have strong evidence that men even caught more colds. So we can't say anything about the effectiveness. So as that follow-up question, we cannot determine for whom the drug is more effective. I'm typing this all up nice and neat because I'm going to upload this document. Okay, one more. Did I not ask for the margin of error on this one? So here, I didn't even ask for it, but remember the shortcut for margin of error, high minus low over 2. There are long ways to get the margin of error, but shortcut's high minus low over 2. Down here, I do ask for it, so we'll actually do it. Okay, first thing we got to determine, hypothesis test or confidence interval. Which kind of problem do we have? It's right there, it's a confidence interval. 1 or 2 groups? It's 2 groups. I've got men and women, male and female students. So this is a 2-prop interval. That's the first thing you decide. That tells you where to go with everything else. 2-prop interval. We're going to define our variable. Let P be the proportion of what? What are we talking about here? Students that did what? Passed the course. These are all really old numbers, by the way. Now we have our 2 groups. Again, everything you see me writing is required on all these written assignments for full credit. So I've got male students and female students. And you can see I've adjusted the numbers a little because I've changed this problem a couple of times. Each group's going to have an X, an N, and a P hat. All right, let's see. Female students, out of 120, 109 passed. For the male students, 79 out of 110. All right, so let's find our P hats, our sample success rates, our sample pass rates. So for the men, 79 out of 110. I'm just around 0.72. Excuse me. And for the women, 109 and 120. 91. I type all my numbers right? Yeah, I think so. 109, 120. Okay, so 0.91. Whoever has a higher P hat is group 1. So the girls are group 1, the boys are group 2. All right, now the calculator is going to do all the work for me. So I want a 2-prop interval. So you just look through all your buttons. Oh, what about button 6? No, that says test. Oh, what about 7? No, that doesn't even say prop on it. It better say prop. Oh, there we go. Button A. It says prop interval. No, that says 1 prop interval. I've got 2 groups. 2 prop interval. And notice when I get in there, look, it's got exactly the numbers I just figured out. It all comes down to knowing what the letters stand for. 109 out of 120 for the girls. 79 out of 110 for the guys. We want a 95% confidence interval, so I'm going to leave that alone. Hit calculate. We're done. Now, here's the hardest part. Writing this out in words. So that's 9% and 29%. I'm just going to round those off. So we got 0.09 to 0.29. Right? Yeah. So we're always talking about how much higher group 1 is than group 2. So it's not 9% of anybody did anything. 29% of somebody did not do something. These are how much higher the girls were than the guys. So our conclusion here is we are 95% confident. The proportion of females that pass the course, their success rate is between, don't forget the word between, that and that, higher than the proportion of men, between 9% and 29% higher than the proportion for men. So if there was a follow-up question, who does better in the class or who passes the class better, we're pretty darn sure it's the girls. By at least 9%, maybe up to almost 30%. By the way, if we had gotten a negative and a positive, that happens. Sometimes you get a negative and a positive. What's it mean to be negative higher than? That would be lower. So like, I'm going to erase all this, but let's pretend for a second that we got a negative here. Then we would have written between 9% right there, lower, and 29% higher. If you get a negative and a positive, then it's between the small one, the negative one lower, up to the positive one higher. Then you can't say who won. If that were the case, I don't know who's higher. Maybe the men won, maybe the women won. But that's not what we got. If you get 2 negative numbers, if they're both negative, you pick the wrong group 1. Start over. Okay, so there's our conclusion. Now let's find our margin of error. Margin of error. Again, we could do it the long way, but the long way on these 2 prop intervals is really long. We don't want that. The short way is high minus low over 2. So 0.29 minus 0.09 over 2. Or if I'm going to use percentages, I could use 29 and 9. Then my answer I would have to write as a percentage. I'm just going to use the decimals here. A lot of mistakes happen here. People will type the following. I want you to watch what I type. I see this all the time. People will type that. That's the wrong answer. I need that top in parentheses. So 2 ways to do it. You can either type the top in parentheses, That's your margin of error, 10%. Or I'm too lazy to do that. I just type the top. Oops. 0.29 minus 0.09. Hit enter and then divide by 2. So 0.1. Notice, by the way, my difference here is about 20 points. So the sample says the girls are about 20 points higher than the guys, plus or minus a little. So like, we're done. That's the end of the problem. I just want to show you that if I were to graph this out, here's P1 minus P2. This is what I'm trying to estimate. The difference between the two, it's about 20% plus or minus some. How much do I have to go up? About 10% up to 29 and about 10% down to 0.09. That's the margin of error right there. That's like about 10%. So the sample says these were 20 higher than this, 0.2 higher, but then I got to leave some wiggle room around that. That's what the margin of error is. So your observed difference will always be smack dab in the middle of this interval. And the margin of error is the distance you went above and below that. And we rounded these numbers, so everything's a little rounded here. Okay. Take this out. All right, I'll upload this document along with, it'll be attached to the announcement for this recorded session. All right, I think that's a good place to stop.